Hello, welcome to this lecture. So our next goal is to study about surfaces embedded in real three-dimensional space. Okay, so in order to do that thing, so we need the concept of differentiability of a function from an open subset of R2 to R3. So for that thing, so we need several variable calculus. So today's lecture is devoted uh, to study several variable calculus. Okay, so let us begin. Okay, uh, so we'll be taking functions from an open subset of some Rn to Rm. Okay, so let us first define what you mean by open set in Rn. So what do you mean by open sets in Rn? Okay, so a set U in Rn is said to be open if for all points x in U there exists a positive number Rx such that so this ball of radius x centered at x is contained in U. Okay, so now what is the meaning of ball? So this is the set of all points or vectors y in Rn such that norm of this y minus x is strictly less than Rx. Okay, so this is the definition of a ball. Okay, so now we are first going to give the definition of directional derivative. Okay, so let us take a function from an open subset U to Rn. So, okay, so maybe first I'll write down directional derivative. So let us take a function. So let f U to Rm be a function. So note that this function, it is a vector valued function. Okay. So this is a vector valued function, meaning that if I take any point x belongs to U, f of x, it is a vector in Rm. So that's why it is called vector valued function. Okay. So f, it is a function from U to Rm. So where this U is an open set in Rn. Okay. All right. So now let us take a point C belongs to U. Okay. Yeah. So this U, it is an open set. So therefore I can get hold of a ball of radius RC around C such that this whole ball is contained in this U. Okay, and this in fact it is a convex set, meaning that if I take any 2 points in this set, so the line joining these 2 points will contain in this ball. Okay. Okay. So this implies that if X and Y, it belongs to this. So if I take the convex combination, it also belongs to this ball. Okay. So where this T is varying from 0 to 1. Okay. All right. So now, so what is the meaning of the directional derivative of f at the point C in some direction? Okay. So let us take, let us take some u be some vector in Rn. Okay. So the directional derivative of f at the point C in the direction u denoted by f prime C u is defined as the following. So f prime C u, so this is defined as, so limit h tends to 0 f c plus h u minus f c whole divided by h. Okay. So whenever the limit exists. Okay. All right. Okay. All right. So now suppose this f, it is a real valued function, means, so suppose f, it is a function from u to r. Okay. It is a real valued function. And now if I take, so let ei to be this unit vector. So this is the this ith position. You have 1 here in the ith position, and rest of the position it is 0. Okay, so ei is this unit vector, and so what will be my f prime c ei? So this, as per the definition, so this will be limit h tends to 0 f c plus h ei minus f c divided by h. Okay, and so now let us take, so let c to be equal to c1 cn. So therefore, so then f prime c ei, so this is limit h tends to 0 f c1 ci plus h cn minus fc1 cn whole divided by h. Okay, so this is the ith partial derivative of this f. Okay, so this is the, so del f del xi evaluated at the point C. Okay, so it is the ith partial derivative of this real valued function. Okay, all right. Okay, so now suppose, so f, now it is a function, it is a vector valued function. It is a function from u to Rm. Okay, so then, so f of any point, let us take x1, x2, xn, it will be like this. So f1, x1, xm, f, sorry, this should be xn, and this is fm, x1, xn. Okay, yeah, so this is this function is described like this. Okay, and what is my f prime c e I? Okay, so c again, it is same as c1 cn, and ei is this coordinate vector. So this is basically is equal to, so partial derivative of this f1 with respect to xi at the point C. Yeah. So f prime ci is this thing. Okay. All right. Okay. So now we have defined directional derivatives. So now suppose all the directional derivative exist. So whether the function is continuous or not. Okay. So in real analysis, we have learned that if function is differentiable, so then it is continuous. Okay. So remark. So for a function f u to Rm, where u it is a open set in Rn, the function, so this function, the directional derivative of this function exists, but the function may not be continuous. So it may happen that all the directional derivatives of f exist at a point C belongs to U, but f may not be continuous. Okay, so for example, if I take this function fxy equal to x y square plus x square plus y to the power 4, where this x is not equal to 0 and it is equal to 0 if x is equal to 0. So you can check that. So all the directional derivatives of f exist, but f is not continuous. Okay, so now so this notion of directional derivative, it is not the derivative of total derivative of f, so there should be something else. So now let me define what you mean by differentiable function. Okay, so we have talked about directional derivatives of a function. So more stronger notion will be differentiability of a function. Okay. So again, in order to define this thing, so let me first tell you, so what you mean by a linear function from Rn to Rm. So a function t from this Rn to Rm is said to be linear. So these two properties are satisfied. If one t of x plus y is equal to tx plus ty for all xy in Rn, and the second thing, t of lambda x is equal to lambda tx. So for all x belonging to Rn and for all lambda belonging to R. Okay. So note that, so you can check this thing. So t of 0 is equal to 0. So this 0, so t of this 0, so it lies in Rn, sorry, and this 0, it lies in Rm. Okay, so this is very easy to check from the property of a linear function. So now let me define what you mean by a differentiable function. So let f u to Rm be a function where u is an open set in Rn. Okay. So f is said to be differentiable at C belonging to U. So if there exists a linear function so this linear function, it depends on the C from Rn to Rm. Okay, so such that the following holds. Such that, so f of C plus B is f of c plus v is equal to f of c plus tc of this v plus norm of v multiplied by this error function. Okay, so where this error function, it tends to 0 as v tends to 0. Okay, so note that here, so c I have taken it to be in u, and earlier I have said that this c will contained inside a ball. Okay, so therefore for some v where norm of v is small, so c plus v, it belongs to this ball. Okay, so whenever norm of v is sufficiently small. Okay, so again note that the c, it belongs to your u, it is a subset of Rn, and b also again it is a b, again it belongs to your u, it is in Rn. Okay, and f of c plus b, it belongs to Rm. All right, and so this ec b, it belongs to your Rm. Okay, all right. So I have defined the definition of differentiability of f if this equation is satisfied. Okay, so this is very important, and so this equation, so star is called first order Taylor's formula. Okay, all right, and this TC is called the total derivative of f at c. Okay, okay, so now let me prove this proposition. So suppose f is differentiable. So suppose f is differentiable at c. Okay, so then so so this directional derivative, so it will exist and it will be equal to the total derivative. So f times cu is equal to tcu. Okay, so this we are going to prove. So this f times cu is equal to tcu. So for all u in Rn, for all directions u. Okay, so what is the proof of this? So f prime c0, okay, So this from the definition, it is clear that this will be equal to 0, and which is again equal to TC of 0. Okay. So now let us take, so let B to be equal to HU, where this B is not equal to 0. Okay. So this will imply that this H is not equal to 0. Okay. And this H, so I have taken this B equal to HU. So this H, it is a real number. Okay. Yeah. So here, so note that. Okay. Maybe I'll just restate this thing. So let us take B equal to HU. So before that, so let us take, so let U be a non-zero vector in Rn. So let U not equal to 0. Okay, so there's a vector in Rn. Okay, and then let us take, so let B equal to HU. Okay, so where this H, it belongs to R. Okay, and H is not equal to 0. Okay, so now let us take this B, the f of C B minus FC. Okay, so this by the definition, we know that the function f is differentiable. So this means that there exists a linear function TC such that this happens. So where this error term, this goes to 0 vector if B goes to 0. Okay, now put B equal to HU. So now we have this equation. Okay, all right. So now this t, it is a linear function. So this h, it is a scalar thing. It belongs to R. So it will come out. So it is h times TCU plus mod h times norm of u times this error term. Okay, and now you divide by h. Okay, and now you what you do, so take limit h tends to 0. So if you take this thing, so this will be equal to TCU, and if I take limit h tends to 0 here, so this whole thing will tend to 0. So mod of h by h, it will be plus minus 1. And so you note that this error term, it goes to 0 as v tends to 0, means h, if I take h tends to 0, v will tend to 0. So this means that error term will tend to 0. Okay, so this will tend to, the whole thing will tend to 0. Okay, so therefore this limit will be equal to this linear function TCU, and the left hand side is nothing but the directional derivative of c with respect to the direction u. Okay, so we have this relation here. Okay, so therefore, so this f prime c, so this you can think as a linear function from this Rn to Rm. Okay, order. So this f prime c, it is also called the differential, is also called the differential of f at the point C, okay, and is denoted as d of f. So d of f at the point C evaluated at the point U is equal to f prime Cu. Okay. So therefore this differential, it is a linear function. So dfc is a linear function. So corresponding to a linear function, so we'll have a matrix. Okay, so what will be the matrix of this differential? Okay. So let us take this u to be u1, un in Rn. Okay. So now, so if I take this vectors, so where this ei is this ith coordinate vector, so this forms an orthonormal basis of Rn. Okay, so this you can write as follows. So summation ui ei I equal to 1 to n. Okay, and so now, so what is my dfc of u? So this is f prime c at the point evaluated at the point u. So this is f prime c summation ui ei. So this f prime c, it is a linear function. So therefore, so what you have here now, so this will be summation I equal to 1 to n ui f prime c ei. So this f prime ci, it is the partial derivative of f, ith partial derivative of f at the point C. Okay. So now again, so this f, so let f, you can write like this, the coordinate functions of f as f1 fm. Okay, so f prime cei, so again it is f1 prime cei fm prime cei. Okay, so this is the partial uh, derivative. So this is my ei. So f del f1 del xi evaluated at the point C, and this is del fm del xi evaluated at the point C. Okay. So this again you can write as this linear combination. So where this G0 Z is this ith coordinate vector in Rm. Sorry, jth coordinate vector. So it is a jth position. Okay. So therefore, so this TFCU is equal to F prime CU. So F prime CU again is this linear combination. So from here, what you will get? You will get this double summation. So you'll get this partial derivative times ui gj. Okay. So this is obtained from the equation star. Okay. So again, so this is nothing but summation I equal to 1 to n. I'm just again writing the same thing. So it is ui multiplied with del f 1 del xi del f. So this evaluated at c, del f del m del xi evaluated at the c. Okay, so which is same thing as if you take this matrix. So if you take this matrix, so this matrix, it is of order m cross n and multiply with this column vector. This is of order m cross n and this is n cross 1. Okay, so this matrix, so this matrix, so del f of order m cross n is called the Jacobian matrix of f. Okay, and now suppose so f is a real valued function. So f, it is a function from u to r, and it is differentiable. At c belonging to u. Okay, so let me state this thing. So a function f is differentiable on an open set if it is differentiable at every points of that open set. Okay, and suppose this function f is differentiable at c. So now, so this is just a real valued function. So you take this differential of this c, of this f at the point c, and so what you'll get, so this will be equal to so we'll get this matrix. Okay, so so this is exactly equal to, so if I take the grad of f and take the dot product with this vector u, and u is equal to u1 un. Okay, so what is my this grad of f? Yeah, so this all these partial derivatives are evaluated at c. Okay, so what is grad of f? So this is del f del x1, this vector, del f del xn. Okay, all right. So now in the next lecture we'll be defining surfaces. So surfaces, how do you define? So you take an open set in R2 and you take a map from that open set to R3. Okay, so if that map is nice enough in the sense that it is differentiable and the differential is injective, okay, and it is also a homeomorphism onto its image, that map. So then, so image of that open set, it will give you a surface kind of thing in R3. Okay, so that we'll do in the next class. Okay, so I'll stop here.